Hello everyone, this is Traveler's Diary. My name is Asis. So this video is the continuation of the video that I presented last time. That's the part 1, and this will be the part 2 of the video where I'm going to talk about the one classical statistical model and one deep learning model. And last time in that part I talked about until up to the data pre-processing part up to data cleaning part. So today I'm going to start with our first model, that is Arima. So let's understand what the Arima is. So Arima basically is a model that is a amalgamation or the combination of three different model, that is AR, that is autoregressive model, MA, that is moving average model, and that is I is integration model. So it's basically a three model combining to form a one model. So autoregressive model is a model that is responsible to understand the correlation between observed value and its lagged value. So it basically makes prediction based on the past values, that is AR model. And secondly, MA model is a model that is responsible to understand the correlation between observed value and its residual. So basically it will predict based on the past error. So this is the second type of model in Arima. And the last is integrated model, that is responsible to make a base fit of line by substitution of the data with the difference term. So for Arima model, it's a classical statistical model. It does not use a machine learning or the neural network, so it is not able to understand data if it is not stationary. So basically I will help the data to make it stationary. So this is the basic definition of Arima model. In Arima, we have three important terms, that is P, D, Q. So P stands for the number of AR term, D is the number of differentiation or the integrations, and Q is the number of MA term. So these three parameters are very important for the Arima calculations. So let's talk about every model in detail in the slides to come. So talking each model in Arima individually, first is autoregressive model. As I already said, autoregressive model makes prediction based on the prior attributes. It will look into the past value. So if we see in this graph on the right, we have a weekly sales data. So the prediction of the next week is made based on the previous data. So past week's data. So basically it will just consider the value of the past week to make the future prediction. So the AR1 model is the model where the next week prediction is made based on only on the last value. The YT is prediction is made based on the YT minus 1, and we have A and B components that are the coefficient in the equations shown. So A and B are the coefficient, and if we see the ARP model, so it will predict the value based on the P past value. So based on the P term, it will make the prediction. And as I've already said, so P is one of the important parameters that is basically the number of autoregressive term, that is how many data we look back to predict the next term. So in AR1 model, so the value of P will be 1, and in the ARP model, the value of P will be P. So this is the autoregressive model in Arima. So secondly, we have MA model, moving average model. So this model is responsible to make a prediction based on the past error. So basically, if we see this, the same graph, weekly sales data, so we have one actual data and we have one predicted data. So what we'll do is it will try to see the error of prediction on the last term, and it will predict the next term. So suppose in MA1 model, it will just see the past error, one step back error, and in MAQ term it will go back to Q term, and it will make a prediction based on that. So basically the Q in Arima model is the number of moving average term, that is how many data the model go and look back to predict the next term. So this is basically a Q term, and that is also very important parameters in Arima model. Similarly, the last term D, differentiation, is also important parameters in the Arima model, because the Arima is a classical model and it is not able to differentiate or deal with the non-stationary data. So this model differentiation is responsible to make the data stationary. So if we see this graph, the data are not stationary. You can see some kind of a trend in the data where it is going, where the value of y is increasing as the value of x increases, and this is the data where the data is quite stationary. So this is the example of stationary and non-stationary of the data. So basically in the differentiation, what is done is, if we see in the column 1 where you have the value x, and it is and the second column or the middle column is the first order differentiation, where the value at the second row is where it will differentiate with the first value of the first row. So this is basically a first order differentiations, so this will helps the data to be stationary. So the D in this Arima model is the order of differentiation. So in the table we can see that the data is quite stationary. The value is between -1 to 0, so the data is quite similar, even after the first differentiation. But if the data is not able to make stationary in the first order differentiation, we differentiate it even twice or thrice, so that the value of D changes correspondingly. So these three P, D, Q are the three parameters in the Arima model. So after we identify the PDQ parameters, so let me just talk about the methodology, how we deal with this model. So we have a historical data, then we do the data pre-processing that I already talked about, then we take the stationary test, and if it is not stationary, we do the differencing, that is the D term. Then if it is stationary, we determine the AR from the PACF chart, and we determine the MA from ACF chart, and similarly we select the optimal parameters and we forecast. So I'll be talking about how we are going to determine the AR term and MA term and the differentiation term. So before that, for the data in the Arima model, we need to differentiate it if there is any seasonality in the data or if there is not any seasonality. So seasonality means like the repetition of data pattern after certain interval of time. So if you see on these two pictures, on the left is a non-seasonal data, because the data is very random. As the time goes on, there is not any trend. But in case of the right image, so there is a trend going upward, and also the data is kind of seasonal, where it goes up and it goes down again, and so on. So so we need to identify this first. So this is non-seasonal data, and this image on the right is the seasonal data. And the equations in for the non-seasonal data is yt is equals to mu plus AR term plus MA term, that I have already discussed. So we need to multiply with the seasonal part of the model PDQ and M if the data is not is non-seasonal, or we can say if the data is seasonal, we multiply with the PDQ. If data is not seasonal, there will be the equations one that will follow. So this is basically we need to keep in mind the seasonality. So where in the seasonal data we have M, where M is the number of period per season. So before we start determining the PDQ parameters, we need to take care of if there is any seasonality or non-seasonality in the data. After that, after we determine if it is seasonal or not, we moved into the Arima model. That's the stationary of the data. So we need to see or check if the data is not stationary or not. So the two images represents the stationary series and non-stationary series. So stationary series meaning that the mean is same throughout the time, and in the non-stationary series the mean and the variance keeps on increasing. So and this is the data, this is the image of our data. So the data is quite stationary, so the mean is quite the same. So so this is the stationary, but if our data was not stationary, what we should do, we should do a augmented decay test. So this is basically a unit root test that will test the null hypothesis, which it consider as alpha is equals to 1. Then we calculate the z-score and we calculate the p-value, and if the p-value is less than 5%, we reject the null hypothesis, meaning that data is stationary. And if the p-value is greater than 5, we cannot reject the null hypothesis, so we conclude that data is non-stationary. So this test is done if the data is not stationary, but for our case, data was pretty stationary, as you can see in the figure and the graph. So we do not have to do this test for our analysis. So after we determine if there is any stationarity and after any seasonality in the data, we move into determining the PDQ parameters. So I already talked about the P as a AR term, D as a differentiation, and Q as a MA term. So basically we determine this parameter based on the Akaike information's criterion number, or the Bayesian information criterion number. So this is basically it is a product of log maximum likelihood multiplied by 2, and we add the number of independent parameters. So this is basically the math behind determining the PDQ parameters. But even with the the autoregression graph or the partial autoregression graph, we can tentatively say what will be the value of the P, D, and Q. So this is the result that was obtained from our code. So we get the Arima PDQ value as 3, P as 3, D as 0, and Q as 5. So let's understand what we can, if we can compare with the graph that I talked about, auto correlation and partial correlation graph. So basically we can also determine this 305 tentatively from this graph. So if we see in the partial autocorrelation graph, so we can see that the first two spikes on the up and the one spikes on the negative side or the below zero side, we have more than 40% correlation in the partial autocorrelation graph. So we can conclude that the P is more than 2, it can be 3, right? So our computational reason gives the value of P as 3. So we can tentatively tell what the value of P would be. And similarly, the value of Q, that is the MA term, we can know how many values are there in the significant threshold, the little shaded color that you can see. So we can make predictions how many value will be. So you can see there's a tentatively 4 to 5 value or the term in there. So we can conclude that the MA term is 4 or 5. And basically in the TD is the differentiation. Differentiation is normally done if the data is not stationary. In our case, data is stationary, so the value of D is 0. So we can differentiate, or we can make a tentative guess what will be the value of P, D, and Q from these graph. But normally the programming or the computation behind the programming basically calculate based on the Akaike information criterion, where it will see the maximum likelihood of the parameter that you choose. So this is way of determining the PDQ parameters. So in a nutshell of the Arima model, we calculate the PDQ parameters as shown in these pictures. So let's go through what we just did. So first we take the data, then we clean the data, then we ensure the stationary of the data. Then what we do is we determine the appropriate P and Q value using ACF and PACF graph, or by the Akaike information criterion model. Or then what we do is we try to predict the best model that gives less error, then we forecast based on that. So this is the basic classical forecasting method. It does not use a neural network, it does not use a machine learning algorithm to understand the pattern. This is like we need to identify or look if there is any non-stationary. So we also it's not completely autonomous systems for the prediction. So this is the model or the mathematical equations for prediction, where it consists of AR term, it consists of an MA term, and also try to see if there is any integrations that need to be done to make the data stationary. So this will be the Arima term, Arima model. So after the classical model Arima, let's move into the univariant LSTM model. So univariant LSTM model is a deep learning neural network. So if I just gave a basic overview what the neural network looks like, so I have pictures of the convolution neural layer where we have a input where it's put to the model, where each model have lots of convolution layers, where each layer is responsible to get the unique features of the model, and each features will be fed as a input to the network, where it passes to the hidden layers, where it will understand the pattern in the data, and the predictions made based on the probability. So this is basically a neural network, and if I represent this with the other schematic representation, it will be the input going into the hidden layer, then it giving the output, and it again updating the updating the parameters. So this is basically like a regular neural network. But if we have something like if we have a data where the value of your prediction not only depends upon the past x, but it will, if it depends upon the y itself, the regular neural network does not work. For example, if someone decides to have Asian dinners all day a week, if he decides to eat Chinese on Sunday, if we decide to eat Korean on Monday, Indian and Japanese, so on, and if the same person and after that, if he again want to repeat the same thing, if he decides to eat Chinese on Thursday, so it's like not every Sunday the person is going to have Chinese. So the what is going to have tomorrow depends upon what he had today, what he is having today. So basically in this kind of data set, it's not that if it is Sunday it's Chinese, if it is Monday it's Korean. It changes every time, so you need to look into what you had yesterday. So this kind of problem, the regular neural network does not comprehend this kind of problem. So we have something called recurrent neural network. What it does is it will go back and it will see what you had yesterday. It will have some memory of what you predict or what you had last time. So the LSTM falls under this recurrent neural network, but it's not it's advanced version of a recurrent neural network, because this RNN had some problem like the vanishing gradient. It's actually a very long topic. I don't think I'll be able to embrace in this video, but this example of the RNN that I talk about, I got it from the internet. So yeah, so basically the LSTM model is a recurrent neural network that's very different from the Arima model that I talk about. So let's talk about how everything works in the LSTM model. So in LSTM model, we have gates that will control the flow of data, the way of processing the data, and the way of giving output. So basically we have a forget gate, we have input gate, we have output gate, and we have a cell state. In forget gate, what we'll do is, this is the first gate in LSTM architecture where information is either forgotten or stored based on the significance of data. So it basically depends upon what will be the output. There's a lot of information in the data, so it will only let it through to the further architecture of LSTM if it is important, or if it is significant in the viewpoint of the output. So basically we have a weight matrix, we have a sigmoid activation functions in there that will responsible to store the data if it is important. And in the input layer, the information goes from this forget gate, and it will try to understand the natures, it will try to understand the features of the data in this model. So, and in the output gate, it will the prediction is made based on the information that you get from the input gate. So all the parameters here are the weight matrix, or the biases, or the weight weight of each gate. So this basically is the architectures of the LSTM model. So talking about the execution steps of LSTM, so as I mentioned in my first part of the video, we have hourly 1 year PV output data, and we divide the data into training and testing data set by removing the noise and outlier in the data. Then what I did was I split the data into 90% training purpose and 10% testing purpose. Actually, the 70% is divided into training, then 20% is done divided for the validation purpose, and 10 is for the testing purpose. So after that, what we do is we use a lot of activation function like sigmoid, softmax, relu. So why we basically do is we do it to normalize the data between specific range. For sigmoid, we divide we range the value between 0 and 1. For relu, we divide the value into 0, -1 to 1. So this is basically making the uniformity in data, and for the model to easily work on the data, we basically use the activation function. And we use optimizer in the data to handle the sparse gradient in the problem. What we do is we use dropout layers. Dropout, basically what will do it will randomly disable the neuron, so that we do not fall into the problem of overfitting of the model. Overfitting basically means that your model works perfectly fine for the training data, but if there is a new data, your model is not going to predict accurately, because that model falsely captures the pattern of your past data that are not very accurate, or that are not as per the trained how it can be in the future. So that's the overfitting. So we use dropout layers, then we use epoch iterations, and we use small batch size, so that the model can accurately understand the data. So this is basically what what the execution steps are. So if I present the result of the Arima, that is the statistical classical model, and the univariate LSTM model, so this is the result you can see. So the first row is the prediction from the Arima model. So you can see the prediction for next 3 days. So this is the next 3-day prediction. So you can see for the first day it is quite okay, but after that it's slowly decreasing. And if we see on the next 5-day prediction, it is pretty bad. And if you see on the 15 days, after 3 days, it's quite like a very straight line. And if we see the univariate LSTM model, the prediction is quite accurate, but it is not able to understand or not able to absorb the unique characteristics of the data. Every time it is just showing a uniform flow of the uniform patterns of the data. So this is basically the univariate LSTM. So we are just considering the one input variable and one output variable. Input variable as a power output, hourly power output, and we are predicting the hourly power output. So that is the result from the Arima and LSTM. So I have a Python code. If anyone needs, I can provide to them, or you can also see in my GitHub account. And so talking about the model accuracy, what we did was we tested the accuracy using the root mean square error, and so this is basically the formula: square root y minus yj, it's actual minus predicted, then we divided with the n. So basically the prediction horizon and the RMSE value as shown in the graph. Using the Arima model, for next 1 day it was 20%, and for the LSTM it was 9, and up to next 15 days the RMSE is 50 and LSTM is 25. So this is basically the model accuracy using Arima and LSTM. And similarly, if we see the comparison of the the model, we can see that the statistical model are easy to use, easy to implement, but it is very ineffective for the long spectrum forecasting, and deep learning models are better to capture intimate characteristics or behavior of the solar irradiation, unlike classical model. And but on the negative side, deep learning model required large training data. It was complex architecture, and it needed the longer computational memory. And if we talk about the accuracy of prediction in the classical model decreases drastically as the prediction time horizon increased, but it was not the same with the LSTM. There was a gradual decrease. So this is basically what the comparison of the the deep learning and the classical statistical model. And this will be the end of this video, and for the next part of the video I'll be talking about 9 different deep learning model, and I'll try to compare and try to see what model gives the best prediction for the solar radiation. So please subscribe my channel, and I'll see you soon. Thank you very much. Bye bye.